All right, I've drawn another circuit right below this so we can compare these. I've put the same devices in there. Okay, I've got my radio, I've got my iPhone, and I've got a light that are in a circuit. But this time, instead of running them all in a row where they all have to depend on the last electricity that's there, we're going to put them in what's called a parallel circuit so that if one of these gets stopped, for instance, the electrons can still have other paths. The key difference between these is if you can only draw one path through this, that's going to be a series. You have to go through every instrument by the same path. Look at these, they have multiple paths. Okay, so we're going to try to figure out, just like we did up here, what's the equivalent resistance so that we can put in 1R for the V equals IR to solve for how much electricity goes through a circuit like this. So this is a series circuit, and this is the parallel circuit. We're going to do the parallel circuit right now. Now, the relationship between how much is an equivalent resistor in parallel circuits is actually a little more complex than the previous one. We just saw that, add up all the resistances and you'll get a total resistance for the circuit. But in a parallel circuit, it comes out a little different, that the equivalent is actually the inverse, or the upside down fraction, of all the inverses of the resistances here. So it's 1/4. You know what, let's write it this way so you see the numbers first. It's 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So the inverse of the total resistance is the sum of the inverses of each resistance. That's such a lot of words in there, but that's the way we're going to solve this. So 1 over the resistance of the total, what we want to use for V equals IR, this was the EQ, sorry, equivalent resistance, is going to be 1/4, right, 1 over 4, plus 1 over 1, plus 1/5. Okay, I take the inverse of all the resistances and then add them up. Well, 1/4 is 0.25. This is just 1 over 1. And 1/5 is 0.2. So I'm going to add those all up. 0.2 plus 0.25 is 0.45, so that's 1.45 is the total. So once you've found the sum of each of the resistances inverses, added up all the inverses, I got a total. That's what the equivalent resistance is 1 over. 1 over that is what the equivalent resistance is. So when I put this into an equation, so I'm going to put the equivalent resistance on this side, 1.45. So 1 over 1.45 is roughly, 1 over 1.5 is roughly 0.66. I don't have a calculator here, but it might be a little bigger. Let's just say it's 0.67 ohms. Okay? I worked that out, put the resistance on this side, put 1 over 1.45. Now in your calculator, that's going to be easy. What you're going to do is you're going to take the resistances, you're going to put that resistance in, you say 1 over that. Put the next put the next resistance in, say 1 over that. Get the last resistance in, say 1 over that, and then you hit equals. When you're done and have that total, then all you do is, it's sitting there as a number, you just hit 1 over again, and it's going to give you out the resistance as you work your way through those. So if this is still 120 volts, let's see what happens to the current in this case. I have 0.67, so I'm going to have to do, can you see, I don't know if I can see this over here. Let's go this way. I'll take this out of here. So let's use that equivalent. Okay, and we want to know what's happening to the current going through this. So it's 120 volts. Let's find out what the current is. This is times 0.67. That's 2/3. So 2/3 of 120. 3 into 120 is 40 times 2 is 80. So now the current in this case, 80 amps. And if you remember, the amps that went through this one is 12. 12 amps went through this circuit. Same exact elements, 80 amps goes through, and that's the danger of those, is that when you put a bunch of things in a a growing set, there's more paths for electricity to flow, and that's fine out here because each one of these actually has a different current flowing through it. when you get to the wire in here, 80 amps flowing through a thin wire, if it's thin, well, those electrons are moving really fast. They'll start the atoms to vibrate. That's called heat. And then you may burn out the wire. You melt the plastic around it. So in parallel circuits, they're great because if one of these gets unplugged or damaged or broken, the others still work. But you do have to be careful a little bit about how fast that current gets going because a bunch in a parallel sort of circuit can have some trouble about burning out wires. Okay, that's how you do the calculations on parallel circuits.